Welcome back. In this video, you will learn how to solve work problems by using calculus. Let's get to it. Alright, so another application of definite integrals is the ability to calculate work done by a force. And so we're entering a little bit into the physics realm here, and so if you've never had a physics course before, this topic might be a little jarring at first, but I promise we're going to break things down to an understandable level, even if you've never had physics before. Okay, and so what work is its energy transferred to or from an object by a force along a displacement. And so in general, work is done by a force when it moves an object. The most simple case of work is when the force applied to an object is constant. And all that means is that the force that we are applying to an object is not changing as we move that object. It is a constant force. And so when the force is constant, we can calculate work with the following formula, that work is equal to the force applied to the object times the displacement or the distance that the object moved from where it started. And so let's take a look at an example problem of this most basic scenario where work is done by a constant force. Okay, so here's our example problem. We want to determine the work done in lifting a 40 kilogram box 3 meters high above the ground. Okay, and so if we want to determine the work, remember that work is equal to the force applied times the displacement or the distance that our object moves. And so in this problem, we're lifting a box that has a mass of 40 kilograms, and we're lifting it 3 meters high above the ground. So we know that the displacement is going to be equal to 3 meters, but what about the force? All we are given here is a mass of our object or our box. We're not given a force. Well, in physics, you learn that force is equal to mass times acceleration due to gravity. And so in this case, we know that the mass of our box is 40 kilograms, but then what about the gravity? What is the acceleration due to gravity equal to? Well, when we're working with the metric system like we are here, since we have meters and kilograms, gravity is equal to 9.8 meters per second squared. And so the force in this example will be equal to the mass of our box, 40 kilograms, times gravity, which is 9.8 meters per second squared. All right, so our work is going to be equal to the force times the displacement, and we have that the force is equal to 40 kilograms times 9.8 meters per second squared, and the displacement is 3 meters. And so if we plug all of that into our work equation, we will have that the work is equal to 40 kilograms times 9.8 meters per second squared times 3 meters. And so if we multiply all of this together, 40 times 9.8 times 3 will be equal to 1,176. And then our units are going to be kilograms times meters divided by seconds squared. So we will have kilograms times meters squared divided by seconds squared. All right, and so this unit right here, kilograms times meters squared per second squared, we actually have a name for this, or a unit of work, that we call joules. And so this will be equal to 1,176 joules, which if you spell that out is Joules, and a joule is the unit of work for the metric system. It could also be expressed as Newton meters, because a Newton is kilogram meters per second squared, and so if you multiply it by another meter, then you have Newton meters. But generally you don't need to know that for these problems, just know that the work unit for the metric system, when you have kilograms times meters squared divided by seconds squared, is a joule. Okay, and so this would be the work done in lifting a 40 kilogram box 3 meters high above the ground. It's 1,176 joules. And so let's look at one more constant force problem. All right, so here's our second example. We want to determine the work done in lifting a 40-pound box 3 feet high above the ground. So this is very similar to our previous example, except our units have changed. Instead of having a 40 kilogram box, we have a 40-pound box, and instead of lifting it 3 meters high, we are lifting it 3 feet high. And so we're not working in the metric system anymore, we are working in the US customary unit system. And so there's a little bit of a difference when you're working with the US units, because in this case, pounds is a unit of weight that already accounts for the effects of gravity. And so if we're going to calculate the work here, remember that work is equal to force times displacement. 40 pounds is going to be our force. Okay, so even though force is equal to mass times gravity, a measurement in pounds already accounts for gravity. And so what that means is pounds is not a unit of mass like grams or kilograms are in the metric system. And so, in this case, our force is going to be equal to 40 pounds. And then our displacement will be equal to the 3 feet above the ground, which is where we want to lift our box to. So we have 3 feet as a displacement. And so the work will be equal to 40 pounds times 3 feet. And that will be equal to 120 foot-pounds. All right, and so in the US customary unit system, foot-pounds is probably going to be the most common unit that you will see for work. You may see some other units, which we'll look at in a second, but 120 foot-pounds is the work done in lifting a 40-pound box 3 feet high. All right, so the most important takeaway here is that a measurement in pounds is a force. So to kind of summarize what we learned from our constant force problems for work, the units of work are as follows. If you're working in the US customary unit system, these 3 units are the most common units of work. We have foot-pounds, inch-pounds, or foot-tons. Sometimes you'll also see mile-tons or mile-pounds, but typically we like to work in foot-pounds if we can. And then for the metric system, the main unit of work is joules, which is the same as Newton meters, which is the same as kilograms times meters squared divided by seconds squared. All right, and so these are the units that we will use when we solve work problems. All right, so we just got done looking at examples of calculating work done by a constant force, but work can also be done by a variable force, a force that does not remain the same throughout the entirety of the problem. It's going to change based on some certain factors. And so when we want to calculate work done by a variable force, we will need to use calculus, or more specifically, a definite integral. And so if an object is moved along a straight line by a variable force, capital F of x, then the work done by that variable force as the object is moved from x equals a to x equals b is this definite integral. The work is equal to the integral from a to b of the force function, capital F of x, times dx. All right, and so this is going to be a very important formula for you to know as you work through different work problems. Now, there are actually several different types of work problems that we can solve by using this definite integral, and we have to approach each of these different types in a different way. And so while that can seem a little overwhelming at first, we're going to take a look at each type of problem one at a time and look at least one example for each type. And so here are the 4 main types of work problems that we are going to look at. There are some other types, but they're very rare, very uncommon. These are the most common ones that you're going to encounter in a calculus course. And so the first type of work problems are spring problems, and that deals with calculating the work done in compressing or stretching a spring. The second type of work problem is a propulsion or gravitational problem, and this deals with calculating the work done by propelling a body into space from Earth's surface. And then our third type of work problem is a lifting problem, and lifting problems deal with calculating the work done in lifting an object where the force required to lift that object is not the same throughout the entire lifting process. And then the fourth type of work problem is a pumping problem, which deals with calculating the work done by pumping a fluid such as water in or out of a tank. All right, and so these are the 4 types of work problems we're going to look at, and so let's get started and look at our first type of work problems. All right, and so the first type of work problem that we're going to learn about are spring problems. And in a spring problem, we can find the work done in stretching or compressing a spring with the help of Hooke's law. And Hooke's law says that the force required to stretch or compress a spring a distance of x from its natural length is k times x, where k is a spring constant. Now, the spring constant is just a measurement of a spring's stiffness, right? How easy or how hard is it to stretch or compress a spring? If you're familiar with springs, you know that some of them are a lot easier to stretch or compress than others. So that's essentially what K is, the spring constant. It's just a measurement of how hard a spring is to stretch or compress. And from Hooke's law, which says that the force is equal to that spring constant times the distance that we want to stretch or compress, we have our force function, capital F of x, which is equal to that spring constant times that distance x. Right, so for example, if we look at a spring at its natural length, like I have right here, and we stretch that to a length longer than the natural length, the distance from the natural length to how far we stretched it is the displacement x in our equation. Now, if we took that spring at its natural length and made it shorter, meaning that we compressed it, the distance from the natural length to the new length, that shorter length, is also the displacement. So it's going to depend on what type of problem you're looking at. Your spring might be stretched or it might be compressed. Either way, the change in its length is your displacement x. Okay, and so where Hooke's law comes from here is that in order to stretch or compress a spring, it's going to require a force because a spring wants to stay at its natural length. So in order to stretch it or compress it, it's going to require a force. And that force is a variable force because it depends on how far the spring was stretched or compressed. All right, and so let's take a look at an example of a spring problem where we will calculate the work done in stretching or compressing a spring. All right, so here's our example problem. We have that a force of 20 pounds is required to hold a spring stretched 5 inches beyond its natural length. How much work is done in stretching the spring from its natural length to 7 inches beyond its natural length? All right, so it's going to be pretty obvious when you have a spring problem. You're going to clearly be working with a spring that is either stretched or compressed. And so in this case, we know that we're going to be using the force equation, that the force is equal to the spring constant times the displacement, right? And then we also know that we're going to want to calculate the work done in stretching the spring, and we know that the work is equal to the integral from a to b of capital F of x, the force function, times dx. Now in this case, the force function is equal to the spring constant times the displacement, but we weren't told what the spring constant is in this problem. And so we need to work with what we are given in order to determine that spring constant so that we can use this force function in this definite integral to calculate the work. All right, and so let's look at what we have here. We're told that a force of 20 pounds is required to hold a spring stretched 5 inches beyond its natural length. So we can use this formula right here and that information to find our spring constant, right? We have a force of 20 pounds required to stretch a spring 5 inches beyond its natural length. The 20 pounds is our force, and this 5 inches is our displacement, right? 5 inches beyond the natural length of the spring. So we'll have 20 is equal to the spring constant times 5. And now we can solve for the spring constant by dividing both sides by 5. And so if we do that, k, the spring constant, will be equal to 4. Now if we were to include units here, this 5 is measured in inches, and this 20 was measured in pounds. So we have pounds divided by inches, and so this would be 4 pounds per inch. Okay, so just keep that in mind. But now that we have the spring constant, we can plug that into our force function, and now we know that the force in terms of x is equal to 4, which is the spring constant, times x. And so we can plug this into our definite integral. All right, but before we can integrate that function, we need to know what our bounds of integration will be. And in order to figure out what those bounds will be, we need to remember what we're calculating here. We want to know how much work is done in stretching the spring from its natural length to 7 inches beyond its natural length, right? And so we will consider the natural length of the spring to be x equals 0, because at the natural length, the displacement is equal to 0. And so that will be our lower bound, and we want to stretch it to 7 inches beyond its natural length, and so 7 will be our upper bound b. So the work in this problem will be equal to the integral from 0 to 7 of our force function 4x times dx. All right, and so now we can calculate the work by solving this definite integral. So we will have that this is equal to the integral of 4x, which if we use the power rule of integration, by adding 1 to the exponent and then dividing by that new exponent, we will have 4x squared divided by 2 evaluated from 0 to 7. And now we can evaluate this expression at 7 and subtract the evaluation at 0. So we will have that this is equal to 4 times 7 squared divided by 2 minus 0, right? Because 0 plugged into this expression is just going to give us 0. 0 squared is 0 times 4 is 0 divided by 2 is still 0. So we don't really even need to write that. We just have 4 times 7 squared divided by 2. And 4 divided by 2 is 2. So this is equal to 2 times 7 squared, which is 49, which is equal to 98. And now we can't forget our units, and so since we are working with pounds and inches, our units are going to be inch pounds. All right, so that is the work done in stretching the spring in this problem from its natural length to 7 inches beyond its natural length. All right, but if you wanted to express this in foot-pounds, remember that there are 12 inches in 1 foot, and so you could divide 98 by 12 to get your answer in foot-pounds. But if your problem doesn't ask you for certain units in your answer, expressing it in inch-pounds is just fine. Let's look at another example of a spring problem. All right, so here's our second example of a spring problem. We have a force of 80 newtons is required to hold a spring stretched from its natural length of 10 centimeters to 15 centimeters. How much work is done in stretching the spring from 13 centimeters to 18 centimeters? All right, and so I don't think I mentioned this earlier, but newtons are the unit of force in the metric system. And so in this case, in order to calculate the work done in stretching the spring from 13 centimeters to 18 centimeters, we first need to know our force function, which requires us to know the spring constant, right? So if we want to calculate the work, that's equal to the definite integral from a to b of f of x times dx, where capital F of x is equal to the spring constant times x. Now, in order to figure out what this will be equal to, or more specifically, what our spring constant is, we will need to use the information given to us in our problem. We are told that a force of 80 newtons is required to hold a spring stretched from its natural length of 10 centimeters to 15 centimeters. And so if we know that the force is equal to the spring constant times the displacement, then we know that 80 newtons will be equal to the spring constant times the displacement. Now in this case, the natural length of the spring is 10 centimeters, and so the displacement from that natural length to 15 centimeters is a displacement of 5 centimeters. Okay, so x is not going to be equal to 15. Instead, it's going to be equal to 5 because that is the displacement in centimeters from the natural length of our spring, right? We're always measuring that displacement from the natural length of the spring. Now in this case, before we solve for the spring constant here, I'm actually going to change the units of our displacement. Currently we're working in centimeters, but if we want to get our final answer for work in terms of joules, remember that we need to be working in meters, not centimeters. And so real quick, 5 centimeters, if we want to convert that to meters, we know that for 1 meter, there are 100 centimeters. And so these units will cancel out. And so 5 divided by 100 will give us that 5 centimeters is equal to 0.05 meters. All right, so 5 centimeters is 0.05 of 1 meter. And so I'm going to use this in this formula instead of 5 centimeters so that we are working in terms of meters, which then will allow us to use the work unit of joules. And so I'm going to erase 5 and write 0.05 meters. All right, and so then we can solve for k, the spring constant. I'll divide both sides by 0.05 meters. And so 80 divided by 0.05 is 1600. And so the spring constant will be equal to 1600. And then the units will be newtons divided by meters. So we will have newtons per meter. Okay, and so 1600 can be plugged in for the spring constant for our force function. So capital F of x is equal to 1600 times x. And then we can use that in our work formula. We just now need to know what our bounds of integration will be. And remember, we want to know how much work is done in stretching the spring from 13 centimeters to 18 centimeters. But remember, the natural length of the spring is 10 centimeters. And so it's not going to be as simple as saying that the work is equal to the integral from 13 centimeters to 18 centimeters. Remember that we are measuring the distance or the displacement from the natural length of the spring, right? So 13 centimeters is 3 centimeters away from the natural length of 10 centimeters. And so that is going to be our lower bound, not 13, but 3 centimeters. And remember that we want to work in terms of meters here, not centimeters. And so 3 centimeters is the same as 0.03 meters if we divide that by 100, because there's 100 centimeters in a meter. And so 0.03 is our lower bound, but then our upper bound, we want to stretch to 18 centimeters, which is 8 centimeters from the natural length of 10. And so 8 centimeters is the same as 0.08 meters, and so that will be our upper bound. We will have 0.08, And now we have our bounds of integration for this definite integral to calculate the work. Okay, so remember that when you are setting up your definite integral, your bounds of integration need to be measurements from the natural length of the spring. All right, so it's important to keep that in mind. But then we can finish setting up this definite integral by plugging in our force function, which is 1600 times x, and then multiply by dx. All right, and so now we can solve our definite integral, and we will have the work done in stretching the spring from 13 centimeters to 18 centimeters. And so this will be equal to 1600 times x squared divided by 2, evaluated from 0.03 to 0.08. Right, so we use the power rule of integration, we add 1 to our exponent, and then divide by that new exponent. Now 1600 divided by 2 is 800, so this is equal to 800 times x squared, evaluated from 0.03 to 0.08. And now if I clean up my work a little bit, we can evaluate this expression at 0.08 and then subtract the evaluation at 0.03. So this will be equal to 800 times 0.08 squared minus 800 times 0.03 squared. Now 0.08 squared is 0.0064, so this is equal to 800 times 0.0064, and then we will have minus 800 times 0.03 squared, which is 0.009. All right, and so 800 times 0.0064 will be equal to 5.12, and then we will subtract 800 times 0.009, which is equal to 0.72, and so 5.12 minus 0.72 is equal to 4.4, and that is measured in joules. That is our unit of work. Since we were working with newtons and we switched from working in centimeters to meters, then we know that our answer is in terms of joules. All right, and so this was our last example for spring problems. Next up, we're going to look at propulsion problems. And in propulsion problems, we can find the work done in propelling or lifting people or objects from Earth's surface or other large masses with a gravitational pull using Newton's law of universal gravitation. Now, if you look up Newton's law of universal gravitation, it won't look exactly like this, but this is derived from that law. And what the law says is that the weight of a body varies inversely as the square of its distance from the center of the Earth. Now, that sounds very complex, but that is all expressed by this force equation right here. The force is equal to c divided by x squared, where c is the constant of proportionality, and x is the distance from the center of the mass. An example of that would be Earth. Okay, and so our force function in terms of x will be equal to that constant divided by x squared. And now let's look at an example of a propulsion problem where we will want to calculate work. All right, so here's our example. We have that an astronaut weighs 150 pounds on Earth's surface. How much work in foot-pounds is required to lift this astronaut 800 miles upward to a space station, assuming the radius of the Earth is 4,000 miles? All right, so the giveaway that you're working with a propulsion problem is when you're talking about the surface of a planet and you're launching an object or a person into space. That's a pretty good indicator that you're working with a propulsion problem. And so in this case, we know that we're going to be using the force equation, that force is equal to c, the constant of proportionality, divided by x squared, where x is the radius of the mass that we are propelling from. And so in order to calculate the work for this example, we will need to use the formula that the work is equal to the integral from a to b of capital F of x, the force function, times dx, and that force function will be equal to the constant of proportionality divided by x squared. And so before we can set up this definite integral to calculate the work, we need to know what that constant of proportionality is. This is very similar to the spring constant. We first need to solve for that constant before we are able to calculate the work. And you're most likely always going to be given something in your problem that will allow you to solve for that constant. And so we're told that an astronaut weighs 150 pounds. That is a force, and he weighs that much on Earth's surface. And we're also told that the radius of the Earth is 4,000 miles. So we can figure out the constant of proportionality between the astronaut and the Earth. And so we know that the force, or the weight of our astronaut, is 150. So we have 150 pounds is equal to that constant of proportionality divided by x, the distance from the center of our mass. Now in this case, that will be the radius of the Earth, right? The radius is a measurement from the center of a sphere or a circle to the outside edge. And so the distance from the center of the mass in this case, which is Earth, is 4,000 miles. And so we'll have 4,000 miles squared. All right, and so now we can solve for our constant of proportionality. We can square 4,000, which if we do that, that is equal to 16 million. And so we'll have 16 million. And then we can multiply both sides by 16 million to get our constant of proportionality. And so C will be equal to 150 times 16 million, which will be 2,400,000,000. All right, so it's a very large number, but that is going to be our constant of proportionality. And so our force function, capital F of x, will be equal to 2.4 billion, or 2,400,000,000. So I'll write that out, divided by x squared. And so we can use that in our work formula. But before we do that, what will our bounds of integration be? Well, our bounds of integration are going to represent the distance that the astronaut is traveling with respect to the center of the mass, or more specifically, the center of the Earth. So the lower bound will be where the astronaut starts. And the astronaut is starting 400 miles from the center of the mass, right? The radius of the Earth is 4,000 miles. And so if he starts on the Earth's surface, then he is starting at a distance of 4,000 miles from the center of that mass. So the work will be equal to the integral from 4,000, and then our upper bound will be the distance from the center where that astronaut is going to be moved to. And we want to lift him 800 miles upward to a space station. So the distance from the center of the mass will be the 4,000 miles, which is the radius of the Earth, plus an extra 800 miles. And so we will have 4,800 as our upper bound, right? So the lower bound is where our astronaut starts, and the upper bound is where we want him to be. Okay, and then I'll plug in our force function. So we have 2.4 billion, so I'll write that out, and that is divided by x squared, and then we're going to multiply that by dx. So we'll have dx. Okay, and so I'm going to clean up my work a little bit, and now we can work on solving this definite integral to solve for the work in this problem. So we could rewrite this to be equal to the integral from 4,000 to 4,800 of 2.4 billion times x to the negative second power, right? We can move this to the numerator by making that exponent negative, and now we can see how to integrate this by using the power rule of integration. So we'll have that this is equal to 2,400,000,000 times x to the negative first power divided by negative 1. And that will be evaluated from 4,000 to 4,800. All right, so we just added 1 to our exponent, so negative 2 plus 1 is negative 1, and then divided by that new exponent of negative 1. Now 2.4 billion divided by negative 1 will be negative 2.4 billion, and so this is equal to negative 2.4 billion, and that is still going to be multiplied by x to the negative first power. However, we can move that to the denominator and make that exponent positive, and so we'll just rewrite this to be negative 2.4 billion divided by x to the positive first power, and that will be evaluated from 4,000 to 4,800. Okay, and so I'm going to clean up my work a little bit again, and now we can evaluate this expression at 4,800 and then subtract the evaluation at 4,000. So this will be equal to negative 2.4 billion divided by 4,800 minus negative 2.4 billion divided by 4,000. All right, now these two negatives will cancel out to become positive, so we're going to have plus that fraction, so I'll write plus. And now negative 2.4 billion divided by 4,800 is actually equal to negative 500,000, and that will be added to 2.4 billion divided by 4,000. And that is also equal to a nice number of 600,000. And so negative 500,000 plus positive 600,000 is equal to positive 100,000. And so if I clean up my work here, positive 100,000 will be measured in mile pounds, since we are working with pounds and miles, and we didn't change any of those units. But remember that our problem wants our answer in foot-pounds, and so we need to make that conversion, which can be done if you remember that there are 5,280 feet in a mile. Most people don't remember that because it's a very weird number to remember. But if we multiply this by 5,280 feet divided by 1 mile, because there is that many feet in 1 mile, our mile units will then cancel. And so 100,000 times 5,280 will give us our final answer that this is equal to 528 million foot-pounds. And that is our final answer. Okay, so that is the work done by lifting an astronaut 800 miles upward from Earth's surface who weighs 150 pounds. And by the way, if you wanted to, you could express this answer in scientific notation if you are familiar with that. If not, not a big deal. Sometimes your calculator will do it for you, but this could also be expressed as 5.28 times 10 to the 8th power, and that would also be measured in foot-pounds. And so that could be another way to express your answer if you like scientific notation, but if not, not a big deal. Both of these answers are correct. Okay, and so with that, that is it for this propulsion problem. We are now ready to look at our next type of work problem. So next up, we're going to look at lifting problems. And in lifting problems, we are going to be calculating the work done by lifting objects where the weight of those objects is not constant. In other words, the force needed to lift those objects is a variable force because the weight of those objects is not the same throughout the entire lifting process. And so this is common when we lift objects such as rope or cables. And so unlike the previous two types of problems, lifting problems don't have a particular force formula that we can follow for every single problem. It's going to require a little bit of intuition, but there is a generic formula that we can try to use in most scenarios. And so here's what that looks like. We know that weight is a force, and weight is measured in pounds. And so we can express that force, or that weight, as a rate of pounds per feet times a distance in feet. And this pounds per feet we typically call a weight density, since it gives us an amount of weight per unit of measurement. And so we can multiply the weight density of an object times the actual length of that object. And so note that this still describes weight, or a force, because when we multiply the weight density by the length, notice that the units of feet would cancel out, and so we'd just be left with pounds, and so this is still a way to describe weight. And so in general, our force formula is going to look something like this. We're going to have capital F of x is equal to some force increment, or weight density, times a distance. And that distance will usually be represented with x. And so whatever our force increment is, or our weight density is, we will multiply that by x, and that will be our force equation. And so let's take a look at an example of a lifting problem where we will use this force function. All right, so here's our example problem. We have a 25-foot rope that weighs 2 pounds per foot is lying on the ground coiled. How much work is required to lift one end 25 feet such that the rope is fully extended? Okay, and so this is a lifting problem where the force varies because we have a 25-foot rope that weighs 2 pounds per foot. When you have a rate like this, that is a very good indicator that you are working with a lifting problem with a variable force. All right, and so if we try to picture what's going on in this problem, we have this 25-foot rope that is lying on the ground coiled, right? So if I just draw this coiled rope here, imagine that this is the rope that we want to lift up. We are going to be lifting this rope into the air by lifting one end 25 feet, right? So we're just going to be grabbing an end of the rope and lifting that up until the entire rope is extended 25 feet in the air. Okay, and so the reason why the force is variable is because as we lift the rope, more and more of the rope is leaving the ground, and so the weight of the rope, or the force on the rope, is going to change, right? When you initially lift up the rope, you're only lifting up a small part, and so that small part only weighs so much. In fact, it's 2 pounds per foot. So as you pick up more and more feet of the rope, as you extend it further up into the air, that rope is going to weigh more. And so because of that, we have a variable force. The weight of the rope is completely dependent on how much of that rope is lifted into the air. If you've ever tried to lift a rope before by just grabbing one end and lifting upwards, you've probably noticed that it starts out pretty light, but as you lift it higher and higher, it starts to get heavier, right? That's a whole lot different than just grabbing the whole rope with both hands and lifting it upwards. We are just grabbing one end and lifting it upwards, all right? If we were just lifting the entire rope at once, then that would be a constant force, but since we're only grabbing one end, then we're working with a variable force. Okay, and so our force function, capital F of x, in this case, is going to be equal to some weight density in pounds per foot times x. And in this case, we know that the rope weighs 2 pounds per foot. And so our force function will be equal to 2x. All right, and so what this represents is however many feet the rope has been lifted, x, we multiply 2 by that height in feet, and that gives us the weight of the rope at that particular height. Okay, but then our work formula is that the work is equal to the integral from a to b of the force function times dx. And so we have our force function, it's 2x, but what about our bounds of integration? Well, our rope is 25 feet long, and we want to lift all 25 feet into the air so that the rope is fully extended. And so our bounds of integration will be from 0 to 25. Our rope starts by lying on the ground, where it is at a height of 0 feet, and we want to lift it up to 25 feet. So we will have that the work is equal to the integral from 0 to 25 of the force function 2x times dx. All right, and so now all we have to do is solve this definite integral, and we will have the work done in lifting that rope. And so this will be equal to 2x squared divided by 2 evaluated from 0 to 25. Right, we just used the power rule of integration. We added 1 to the exponent and then divided by that new exponent. And then these 2's are going to cancel. And so this is equal to x squared evaluated from 0 to 25, which if we evaluate that, it will be equal to 25 squared minus 0 squared. And that will be equal to 25 squared, which is 625 minus 0. And so 625 is our work, but we still need units. And so since we're working with pounds and feet, we know that the work done is 625 foot-pounds. And so that is the work done by lifting the rope in this example. Let's look at another example of a lifting problem. All right, so here's our next example. We have a cable that weighs 3 pounds per foot is used to lift 1,000 pounds of iron ore up a mine shaft which is 3,000 feet deep. Find the work done. All right, so I'm going to start by drawing a picture of our scenario here. Let's imagine that this is our mine shaft, and at the bottom we have our iron ore. This is a very bad drawing, but there's the iron ore. And that iron ore is attached to a cable that we are going to use to lift the iron up out of the mine shaft. And so remember that this mine shaft is 300 feet deep, and that means that the surface would be 0 feet deep. All right, and so we have a variable force here because this cable weighs 3 pounds per foot. The weight of the cable, or the force on that cable, depends on how much of that cable has been lifted. And so the force function, in this case, will be equal to the weight density of that cable times x. And the weight density is 3 pounds per foot. So if we're looking for a rate in pounds per feet, and we're going to be multiplying that by x, then our force function is equal to 3 pounds per foot times x. However, in this case, that is not our entire force function, right? In this case, we're not only lifting the rope, we are also lifting up 1,000 pounds of iron ore. Now, unlike the rope, the force on that iron ore is constant throughout the entire lifting process. The iron ore is not getting heavier and it's not getting lighter. It is a constant weight of 1,000 pounds. And so unlike the weight of the cable, which is variable, this weight is constant. And so we're just going to add that 1,000 pounds to our force function, right? So we're going to have the variable force for the cable plus the weight, or the force, on the iron ore, which is 1,000 pounds, and that is constant. All right, so our force function is equal to 3x plus 1,000. And so now we can set up our integral for work. We will have that the work is equal to the integral from a to b of the force function times dx. And so we have our force function, but what about our bounds of integration? Well, we are lifting the cable and the iron a distance of 300 feet, since the mine shaft is 300 feet deep. And so even though I have this labeled as 300 feet deep, the iron ore and the cable are starting at a height of 0 feet that they have been lifted, but then at the end, they are going to be lifted a total of 300 feet to get to the surface. So our bounds of integration will be from 0 to 300. So the work is equal to the integral from 0 to 300 of the force function 3x plus 1,000 times dx. And so now we have our definite integral set up that we can solve to find the work done in this scenario. And so if I clean up my work here, we can integrate each of these terms, and this will be equal to 3x squared divided by 2 plus 1,000 times x evaluated from 0 to 300. Right, so we use the power rule of integration on 3x, so we add 1 to the exponent to get x squared, and then divided by that new exponent, and then the integral of 1,000, which is a constant, is equal to that constant times x, the variable of integration. And so now we can evaluate this at 300 and subtract the evaluation at 0. However, notice that when we plug 0 in for x here, that's just going to produce 0, because 0 squared times 3 is 0, divided by 2 is still 0, and 1,000 times 0 is also 0. So all of this is 0, so we don't need to worry about plugging in 0. Let's just plug 300 in. So this will be equal to 3 halves times 300 squared plus 1,000 times 300. And then if you want, you could write minus 0, but we don't really need to write that since it doesn't affect our calculation. All right, but then 300 squared is 90,000. So this is equal to 3 halves times 90,000. And that will be added to 1,000 times 300, which is equal to 300,000. And so if I clean up my work here, 3 times 90,000 is 270,000, and so this is equal to 270,000 divided by 2, and that is added to 300,000, and 270,000 divided by 2 is equal to 135,000. And so if we add 300,000 to that, our final answer of work will be equal to 435,000. And our units in this case will be foot-pounds since we are working in terms of feet and pounds. And so 435,000 foot-pounds is the final answer for the work done in this problem. All right, let's look at our next type of work problem. So the last type of work problem that we're going to look at here are pumping problems. And these can sometimes be the most difficult type of work problem due to the formula, which we will look at in just a second, but it's actually not as complicated as it seems. But in pumping problems, we are trying to find the work done in pumping a liquid or a fluid, such as water, in or out of a tank. And so to do that, we consider the incremental force on very thin slices of water throughout the tank. And I know it sounds weird to say slices of water, but if you imagine, if we were just to look at one small slice of the tank that is filled with water, we can look at the work done in pumping just that single slice out of the tank and then integrate that force for the entire depth of the water, and that will give us the work done in pumping all of the water out of the tank. All right, and so for pumping problems, our work formula is going to look a little bit different. Our definite integral is going to change. Instead of having the integral from a to b of a force function times dx, we're going to have the following. We're going to have the density of our liquid times gravity, or together the weight density of that liquid, times the integral from a to b of the cross-sectional area of one of the slices of water times delta x, or the distance that that slice of water would need to travel in order to be pumped out of the tank, and then times dx, which would represent the height of the slice. Right, so if we're looking at our slice in the tank here, this thickness or this height would be dx. And so then the cross-sectional area, capital A of x, would be the cross-sectional area for our slice. So in this case, our slices have cross-sections that are circles, and so the area would be equal to the area of a circle. And then for the distance to pump delta x, if we're choosing this particular slice that we're looking at to be a distance of x from the bottom of the tank, then this distance from the top of the tank to that slice is the distance delta x that the water slice would need to travel to be pumped out of the tank. All right, and then finally the weight density is going to be dependent on what fluid you are working with. Now in most cases that's going to be water, and so it can be helpful to actually memorize the weight density of water. And so if you're working in the US customary unit system, the weight density of water is 62.4 pounds per cubic foot. But if you're working in a metric system, then the weight density of water is 9,810 newtons per cubic meter. All right, so you might want to write these down because pumping problems, more often than not, are going to deal with water in a tank. And if it's working with any other fluid, your problem is most likely going to tell you what the weight density of that liquid is. All right, but back to our formula. We've now gone through every part of this definite integral as it pertains to a pumping problem with this picture over here, where we want to pump this water out of the tank. And so before we look at an example problem of using this formula to calculate the work done in pumping water out of a tank, I just want to quickly show you where this formula comes from. And so remember that work is equal to force times displacement, and we know that force is equal to mass times acceleration, and acceleration can be replaced with gravity, since gravity is a form of acceleration. And so we can replace the force in this work formula with mass times gravity, and so work will be equal to mass times gravity times displacement. And then we also know that density is equal to mass divided by volume. You may have come across this equation in a chemistry course or a physics course. And so if we solve for mass by multiplying both sides by volume, then we know that mass is equal to density times volume. And so we can replace mass in this equation with density times volume. And so we'll have that work is equal to density times volume times gravity times displacement, which we can then reorder to have that work is equal to density times gravity times volume times displacement. And then this volume corresponds to the volume of the water in the tank. And so we can represent that volume with the definite integral of the cross-sectional area of that volume from A to B, where A and B represent the depth of the water, and then multiply that by the height of each disk or cross-sectional area of that volume. And so that would look like this. The work would be equal to density times gravity, or the weight density, times the integral from A to B of the cross-sectional area times dx, and that would still be multiplied by the displacement, but that displacement is going to rely on each cross-section or each slice of the volume. And so I just like to rewrite this to be delta x for the displacement and then times dx. All right, and so that's where this formula comes from. This is the same thing that we have right here. And so I thought it might be helpful to see where that comes from, as it might help you understand better how we're calculating the work in these pumping problems. All right, and so with that, let's look at an example problem. All right, so here's our example. An open tank filled with water has the shape of a right circular cone. The tank is 8 feet across the top and 6 feet high. How much work is done in emptying the tank by pumping the water over the top edge? All right, and so the first thing that you should do here is draw a picture of your tank. So in this case, we're told that it is the shape of a right circular cone. And so that will look something like this. There's the top of our cone, and then here are the sides of the cone. All right, and so we're told that this tank is 8 feet across the top. So I'll label that. This is 8 feet, this distance right here, which by the way means that our radius of our cone is going to be 4 feet, because that's half of 8 feet. And we also know that the tank is 6 feet high. So we know that this distance right here is 6 feet. All right, and then we also know that this tank is filled with water, and so I'm going to represent that by shading in the entire cone so that we know that the entire tank is filled with water. All right, so let's write down our work formula, or our definite integral, so that we can begin figuring out how to set it up and solve for the work in this example. So the work is equal to the weight density times the integral from A to B of the cross-sectional area of a slice of the water times delta x, or the distance that the water needs to be pumped, times dx, the height of one of our slices. And so let's take a look at a slice of this water. Right, so if we look at a slice right here, let's look at this part of the water. Let's say that that disk is a measurement of x from the bottom of the cone, or the bottom of the tank. We want to know what the cross-sectional area of that disk would be. Well, we know that the cross-section here of this cone is a circle, and so we at least know that the cross-sectional area will be equal to pi r squared, since that is the area of a circle, but we don't know what the radius is for this slice, right? This distance right here would be the radius r, but we don't really know what that is, right? Because as we would look at more and more slices of water throughout the entirety of this tank, that radius of that slice is going to change depending on where that slice is within the tank. It's not going to be a constant radius because the tank is shaped like a cone. But what we can do is represent the radius in terms of x by using similar triangles, right? So remember that we know that the height of the cone is equal to 6 feet, and so we can draw one triangle to represent the tank and then a smaller triangle for our slice. So we're going to have two triangles that look like this. if this triangle corresponds to our cone, then the radius, or that top part of the triangle, is 4, and the height is 6. And then for our smaller triangle for the slice, the measurement on the top, or the radius, is r, and the height is x, right? We chose that slice to be a distance of x from the bottom of the tank. And so now we can use similar triangles by saying that 4 is to 6 as r is to x. And that looks like this. 4 is to 6 as r is to x. And so now we can solve for the radius by multiplying both sides by x, and we'll have that the radius is equal to 4/6 times x, and 4/6 will reduce to 2/3, and so the radius is equal to 2/3 times x. And now we have expressed the radius in terms of x. And so if we go back to our cross-sectional area, the cross-sectional area of one of these slices of water will be equal to pi times 2/3 times x squared. All right, so that's the cross-sectional area. Now we just need to determine what delta x is. How far does our water need to travel for each slice of water? Well, if we're looking at a slice of water that is a distance of x from the bottom of the tank, then this distance that it needs to travel would be 6 minus x, right? Whatever this distance is here for each slice is going to be equal to the difference between the entire height of the tank and whatever value of x you were at for that particular slice. And so delta x is equal to 6 minus x. All right, and so now we have pretty much everything we need to know to set up this definite integral. We just need to figure out our bounds of integration, and then of course we know that the weight density of water when we're working with feet will be 62.4 pounds per cubic foot, but we'll get to that. Let's figure out our bounds of integration first, and the bounds of integration are just going to be the range of our x values, right? How much water do we need to pump out? Well, we need to pump out the water from x equals 0 to x equals 6 because that whole tank is filled. So we know that our bounds of integration will be from 0 to 6. So we can now finally set up this definite integral, and we will have that the work is equal to the weight density of water, which is 62.4, since we're working with feet, or the US customary units, times the integral from 0 to 6 of the cross-sectional area, which is pi times 2/3 times x squared, times delta x, which is 6 minus x, times dx. Okay, and so now if I clean up my work here, we can begin solving this definite integral. And so let's start by simplifying it a little bit. We can square our radius here and then pull pi outside of the integral. So the work will be equal to 62.4 pi times the integral from 0 to 6 of 2/3 squared, which will be 4/9 times x squared times 6 minus x times dx. Now we can pull this 4/9 to the outside as well, and then we can distribute x squared through this quantity. So we will have that this is equal to 62.4 times 4 pi divided by 9 times the integral from 0 to 6 of 6x squared minus x cubed times dx. Right, we pulled 4/9 to the outside, so we have 4 times pi divided by 9, and then times 62.4, and then x squared times 6 is 6x squared, and x squared times negative x is negative x cubed. Okay, and so now at this point, we don't really need our drawing of our cone anymore, and so I'm going to erase that, and we're going to spend the rest of the time solving this definite integral. All right, and so if we integrate each of the terms in this definite integral by using the power rule of integration, we will have that this is equal to 62.4 times 4 pi divided by 9 times 6x cubed divided by 3 minus x to the 4th power divided by 4 evaluated from 0 to 6, right? So we add 1 to each of these exponents and then divide by their new exponents. Okay, and so 6 divided by 3 is equal to 2, so we can rewrite this to be 2x cubed. So I'll have 2 times x cubed, and now we can evaluate this expression at 6 and subtract the evaluation at 0. However, note that plugging 0 into each of these terms is just going to produce 0. 2 times 0 cubed is 0, minus 0 to the 4th power divided by 4 is also 0. And so we just need to plug 6 into each of these terms. So this will be equal to 62.4 times 4 pi divided by 9 times 2 times 6 cubed minus 6 to the 4th power divided by 4, and then you can subtract 0. Okay, and so if I clean up my work, this is equal to 62.4 times 4 pi divided by 9 times 2 times 6 cubed, which is 216, minus 6 to the 4th power divided by 4, and 6 to the 4th power is 1,296, and that will be divided by 4. And then 2 times 216 is 432, so I'll just rewrite that. That is going to be 432. And then 1296 divided by 4 is 324, and so I'll rewrite that. That will be 324. And then 432 minus 324 is 108. So let's rewrite that, and we will multiply by 108. Okay, and so now 108 divided by 9 is equal to 12. So this is equal to 62.4 times 4 pi times 12. And then 12 times 4 is 48. So we could rewrite this to be 48 pi. And then 48 times 62.4 will be equal to 2,995.2. And that's still going to be multiplied by pi. All right, and so this is the work done by pumping the water over the top edge of the tank in this problem. We just need to remember our units of foot-pounds, since we were working in terms of feet, and our weight density was water in terms of pounds per cubic foot, and so that is our final answer for the work in this problem. If you multiplied pi times 2,995.2, you can have another answer of 9,409.7 foot-pounds, but either answer is correct. I usually choose to just leave the pi there rather than multiply it through so that I have a nicer answer. All right, and so with that, that was the last example and last type of work problem that I wanted to cover in this video. If you want to see some more examples for all the different types of work problems in this video, feel free to check out my examples video that I'll have linked at the end of this video as well as in the description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.